This topic is forces in circular motion. We're going to begin with a kind of like a rule. Um, any object moving along a curved path is accelerating towards the center of curvature. So here I've drawn a small picture. This dot right here, this object is moving along a curved path. Here's the center of curvature, and we've drawn an arrow and labeled it as the acceleration, which points towards the center of curvature there. This acceleration is called a centripetal acceleration, which centripetal means center seeking. And this centripetal acceleration will cause the direction of the object to change. Remember that acceleration is the rate of change of velocity, and velocity includes both speed and direction. We've seen how in kinematics, how the acceleration will cause the speed of an object to change, but now we're looking at how the direction can change. And so there is a way to calculate the centripetal acceleration. Lowercase a subscript c is v squared over r. This is the centripetal acceleration in meters per second squared. V is not the velocity, but the speed of the object in meters per second. And r is the radius of curvature, which is in meters. We'll come back to this equation shortly. Let's go to an example. Let's imagine that we are twirling a ball on a string, a ball at the end of the string. We're twirling it around vertically like this. And so it goes here and it goes around like that. And so it has a circular motion. Okay, the ball has a mass of 0.4 kilograms. At this location, at the bottom of this path, the speed of the ball is 8 meters per second, and the length of this string is 1.6 meters. For the length, we'll use a cursive lowercase l. And the first thing we want to do here is draw a free body diagram. And so, for the ball at this location. So I would encourage you to take a moment and pause the video and draw what you think it looks like, and then compare it with the video when you're ready. So the ball has mass. It has a gravitational force, mg, and it is attached to a string, so there has to be a tension force. And so think about whether that tension force should go up or down. And I'll ask a question to remind us, is the ball accelerating? Think about it. Is the ball accelerating here? And, well, you can go back up here and see that any object moving along a curved path is accelerating. And it's accelerating towards the center of curvature. So, from this location, the ball has a centripetal acceleration that's pointing towards the center of this circle. And so it must have a centripetal acceleration pointed up. And so that means that the tension force, not only is it here, but it must be longer than the gravitational force to show that there's more magnitude there. Another way of thinking about the direction of the tension force is, of course, that a string can only pull. So the string is pulling the ball up. It cannot push on the ball down in this case. For part B, let's figure out the magnitude of the tension force. We're going to use Newton's second law, which is for F equals ma, but it's a sum of forces equals ma, but it's a centripetal acceleration. And me personally, I like to write the subscript c to remind me that I'm going to be substituting this in to the equation. So let's do that. You could make it look like this, m times v squared over r, but the m can just come upstairs with the um, speed. So we're going to write mv squared together over r equals the sum of the forces. We'll put tension force first, subtracting mg, and of course to get ft isolated, we will add mg to both sides, and from here we will substitute our numbers. The mass is, I believe, 0.4, and the speed is 8 squared over the radius, which is 1.6, plus 0.4 times 10 is 4. And so let's go ahead and calculate this. And I'm getting 20 newtons of force. Okay, I'm looking around. I don't see anything I forgot to mention. Um, I will just say, for there to be a centripetal acceleration, there must be a net force pointed towards the center of that circle as well, which we've seen here. There was enough tension force to provide a net force upward. Okay, let's try another one. I think the next one, yeah, is the same ball. Not the same ball, but it's a same situation where a ball is moving around in a circular path. The mass is 0.60 kilograms. It's moving in this direction with a speed of 9 meters per second at the top of that path, and the length of the string is 1.2. Let's draw the free body diagram, and again, I encourage you to try this on your own, pause the video, and test yourself to see what you come up with to draw the free body diagram. And so let's continue. Of course, there will be a gravitational force mg pointed downward, as we always kind of do. And the tension force. Remember, a rope cannot push on the ball, it must pull, so it is pulling it down. And I will make the tension force a different length, just so we don't think that they are equal in magnitude. Cool, and this works out. There must be a centripetal acceleration pointed downwards, pointed towards the center of that curved path. And that one's done. Let's continue with part B and figure out the tension force once again. F equals ma. Sum of forces equals ma. We'll write Ft plus mg equals mv squared over r. And of course, to isolate t, we will write mv squared over r. Of course, we subtracted mg from both sides. This is 0.6, 9 squared over 1.2. And of course, I failed to mention that the length of the string will be the radius of this of the curvature here, which I'm sure many of you would have figured out. And it's 0.6 times 10, we'll just say 6 here. And I'm just calculating 1.2 minus 6. 34.5 newtons. We'll box that in. Cool, everything looks good to me. Did we box in our answer? Yeah, we did. Cool, those are two examples. Let's go on to a third. This one is a little bit different. And of course, I've given away the secret for part B. But anyway, we're going to keep going. What we have here is a bowl, and I drew this really fast earlier today, so you'll have to excuse it. But this is supposed to be a bowl. This is the top of the bowl, of course. Here's the curve. And we have a ball that's rolling in the bowl. And you can imagine it starts here maybe and rolls around this way, rolls back and forth. But for the problem, we're looking at where the ball is positioned at the bottom of the bowl. It's moving with a speed of 3 meters per second. The mass of the ball is 0.4 kilograms. And the radius of curvature, which I've drawn here, probably too high. But regardless, the radius of curvature is 0.5 meters. We'll start by drawing a free body diagram for the ball at this point. And of course it has gravitational force mg. It must have a larger magnitude force pointed towards the center of curvature. Of course, didn't draw it very well. And that force is from the surface, which is a normal force, Fn. I'll just note that, I was looking at what some students had written down. Because the ball has a velocity, some of us think that there must be a force pushing to the right, but nope, there is not. Nothing is pushing it to the right in this case, right? The only forces that are pushing on this is the bowl pushing upward and gravitational force pulling downward. Let's, for part B, let's figure out the normal force. And so we'll write the sum of forces equals ma. Which is mv squared over r. And we will put in our forces. Fn goes first, minus mg. We've seen this, or similar to this, mv squared over r plus mg. And now we will substitute our numbers, 0.4, not 9, but 3, squared, 0.5, plus 4. You can take the time to be trying this yourself. Going through the motion of calculating this, still learning there. You're still learning by trying this on your own. 11.2 newtons. Yeah, I'll have some students that look at this and they're like, of course I can do that. And then the first time they try it, they forget the squared, or they have a situation here with parentheses, maybe the decimal gets left out. Okay. It's good to just always practice this. Cool. Don't think I need to say anything else here. We could have drawn upward acceleration there, which makes sense in this free body diagram. And again, just to show you, many different kinds of forces can provide a centripetal acceleration. We had tension, gravitational. Here in this case, the normal force would contribute to that centripetal acceleration. Cool, and I think we can continue. Let's do the last one. Okay, let's draw something here. So what we have is a coin on a turntable, and the turntable is spinning a record player, right? A record player. So imagine a record player, and you have a coin sitting on the disc there, and it's turning. This is the axis of rotation for the turntable. The coin is right here. It's placed a distance d of 0.12 meters, in other words, 12 centimeters, from the axis of rotation, and it's spinning this way. This is a side view, and go ahead and take some time to draw that. If we gave it a top view, see if I can try this here. Cool, okay, shaded it in, I guess. Here's the axis of rotation there for the turntable. Here's the coin. And as this coin goes around, it will carve out a path, not carve out, but we're kind of tracing its path here. It would be a smaller circle within that turntable. The radius of that circular path, is, of course, the distance d. Okay, and of course it's turning this way. Let's draw a free body diagram for the coin. On this turntable, and we'll use the side view to draw this free body diagram. Of course, it's got gravitational force mg, it's got normal force Fn, which are equal in magnitude. The coin will not be accelerating up or down. And so the coin is going in circular motion, and so there must be a centripetal acceleration pointed towards the center. There must be a net force pointed towards the center of that circle, of that circular path. And so there is a force here that's pointing it in. And so we have to think about what force is the one that's giving it a centripetal acceleration, which of course has to be a friction force. So to think about that, you can suppose that there was no friction. What would that coin look like? It would look like one of two things. If the coin was already moving in a circular path and all of a sudden the friction went away, at this point here, the coin would move off in this direction with some speed in that direction. If there was no friction, it would just slide off. Or if it started rotating and the coin was there and there was no friction, it would just kind of stay there and the turntable would spin underneath it. It would just stay in that spot without any friction. You need that friction to get it to move. And of course, this is a static friction. It's not slipping while it's on the turntable. Pretty easy to imagine. So that's the free body diagram. And now we want to figure out the speed of the coin. That's the next question. So to get into the speed, I have to talk a little bit about this. This coin on the turntable is actually a special case of circular motion. It's uniform circular motion. In other words, the speed of the object is constant. And we have an equation for this. The speed is equal to 2 pi r over the period. So we're going to talk about all this. V is the speed. 2 pi is just a number. R is the radius in meters. Of course, this is meters per second. And T is, it is, but it isn't the time. Lowercase t time is any amount of time. If you remember kinematics, it could be where's the object after 1 second, after 10 seconds, whatever. T is just any amount of time. But for uniform circular motion, this is actually period. And I should say capital T we often use for period, which is a time, it is in seconds, but it's the amount of time that it takes for an object to go, well, I wasn't trying to do that. Let's see here. Okay, good, we got rid of it. It's the amount of time it takes for an object to go around the circle once, or in other words, did it again. Around the circle once, which we call a revolution. It's how much time it takes to go around exactly once. And so let's write that right here. This is the time required for one revolution, which of course is in seconds as we wrote. So this equation makes a lot of sense if you know the basic equation for speed is distance over time. The distance let's think about the coin. The distance that the coin travels here is the circumference 2 pi r of the circle. And the time it takes to do this, well, that's the period. It's the time it takes for one revolution. Cool. And so we can use this. By the way, the other examples are not uniform circular motion. For example, this ball rolling in the bowl would be going fastest at the bottom of the bowl, would be going slower as it comes back up to the edges of the bowl like this. So these were not uniform circular motion, but this one is. So as the coin goes around this turntable here, it's going at a steady rate at a constant speed. Let's do part B, which is 2 pi r over period, 2 pi times the radius over the period 1.8 seconds, which of course I did not mention until now. And so let's calculate this to, and of course, where is pi on this calculator? There it is, and then we get 0.419 meters per second for the speed of the coin. Cool, we'll box it in. Now, what do we want to know next? I think we want to know, what is the friction force? What's the magnitude of the friction force on the coin? So let's do this. Let's use Newton's second law, which is mv squared over r. Now, what force or forces is contributing to that centripetal acceleration? Well, it's all friction force. It's all the friction. So we're just going to write the friction force here, which of course is a static friction. And all we have to do is plug in some numbers. The mass of the coin, 0.04. The speed is, as we said, 0.419 squared over the radius, this. So let's square that. Let's multiply by this and divide by that. Let me calculate that again. Well, I'm going to say this gives me 0.0585 newtons of force. 0.0585, yeah. That's the friction force. Now, last question D. What is the minimum amount of static friction so that the coin does not slip? Or the coin does not start to move, you could say. And so we'll do part D down here. Yeah, let's say it does not start to move. All right. We know our equation for static friction is less than or equal to mu sub s Fn. And because this is a minimum type of question, we can get away with an equal sign here and times Fn. The normal force, as we can tell by the free body diagram, is equal to mg. So this becomes a very simple calculation here. We just need to take the friction force over mg to give us mu sub s. We just divided both sides by mg. And so we will divide 0.0585 divided by 0.4. 0.0585 divided by 0.4, and which is 0.146. Cool. Just looking it over, want to make sure I have not forgotten anything. Um, this equation only works for uniform circular motion. Okay. In other words, when the speed of the object is constant as it goes in that circular path. So this only works for uniform circular motion. This one works for all circular, any type of circular motion. So we'll just keep that in mind. Anyway, that's it.